Let's look at one other special case that will be quite familiar to us. So again, we have our input layer where we're doing a super simple neural network where all we have is, again, the bias term and a single regressor. And then we have, in this case, an output layer, and that our output layer is a binary classification task. So all we want to do is predict yes or no. So imagine our previous example that we were talking about where our X was the mass of a diamond, let's say. And then our output layer is whether the price is above, I don't know, let's say $500. Because you're a diamond merchant and you don't even want to bother to look at a diamond if it's worth less than $500, let's say. Okay. We might, if we were not thinking about neural networks, we might model some data like this as logistic regression. And it turns out that logistic regression is simply a special case of neural networks. Okay, so how do we have to adapt what we previously did? Well, remember, our diagram doesn't show many components of the actual model being fit. For example, there's two weights here, where there's always going to be weights connecting the nodes to, whenever there's a edge connecting a node to a next layer, there's going to be an associated weight with that edge. So we have two weights right there that aren't indicated. And then we have our output activation function. So in this case, our output activation function is going to be the so-called sigmoid function. That's one example of something we can do. And the sigmoid function looks something like this. F of A is equal to e to the a over 1 plus e to the a. So that's a function that looks like this, where it doesn't go back down. It stays up like that. So it limits towards 1 in that direction, and it limits towards 0 in this direction. Okay, so that's 0 on the y-axis, and this is 1 on the y-axis. Okay, so what's nice about our sigmoid function is it converts a, which might be a number that could be extremely large or extremely small, and it converts it into a number that's between 0 and 1. So what we're thinking is that we are modeling, say, the probability that our outcome is 1 given our regressor, okay? And so that our model for that is that we're going to take these linear weights and add them together, take the result, apply the sigmoid function to it, and that will be our predicted value. So what I'm suggesting is that y hat is the function f, the sigmoid function, of our input layers times their weights. So these little x's are multiplication, and the big X is the predictor. Okay, so this is going to be equal to e to the w naught plus w1x over 1 plus e to the w naught plus w1x. Now at this point, it's still not logistic regression, because remember, there's one other thing we have to specify, which is the loss function. So it turns out if you do a loss function called cross entropy, that is equivalent to maximizing the likelihood associated with Bernoulli outcomes, which then is exactly logistic regression. So if y hat is the estimated probability of if y hat is the estimated probability of a 1, then what we're trying to maximize in this case, or we'll minimize the negative of this, is the Bernoulli likelihood function, which would take this as the probability, which is e to the w naught plus w1x over 1 plus e to the w naught plus w1x, raise it to the yi power, okay? And then it would take 1 minus this quantity. 1 minus this quantity, you can work out the math, but I'll just tell you, it works out to be this, e to 1 over 1 plus e to the w naught plus w1x. raised to the 1 minus yi power. And then this tends to not be super stable, so people have a tendency to take the log of it. And then we typically in machine learning, we talk about loss functions, not trying to maximize the likelihood, so we put a negative there. And that is the log of the Bernoulli likelihood. That works out to be exactly what the algorithms are calling cross entropy, and we'll tie it directly to the notion of cross entropy later on. But at any rate, the larger point I'm hoping you're getting away from this little lecture is that logistic regression, a simple logistic regression, is exactly a special case of a neural network with a diagram that looks like this, where you've specified a specific output activation function, namely the sigmoid function, and then you've specified a specific loss function, specifically the cross entropy loss, or what works out to be equivalent to the negative log likelihood that we would maximize if we were doing logistic regression directly. Okay, so that's another special case. And then after this, we're going to start talking about when we have more regressors, and then we'll move on to adding hidden layers.